Welcome. This is a podcast, meaning it will primarily be audio, however the visual backdrop will change a bit more frequently. Well, to answer the question in the title, just to start off with, theoretically anything's viable if the price is high enough. But is the price high enough? Or what would it have to be in order to get high enough? Well, let's go ahead and find out. That's right. Any longtime viewers, you know, it's that time again. Time for Let's Do the Math. And by us, I'll do the math. All you have to do is watch a video. Except this time, instead of an Excel spreadsheet, you get space pictures. So there've been a few asteroid and comet sample return missions carried out by space agencies. Usually, however, only designed to and capable of collecting small sample sizes, a few hundred grams, maybe a few kilograms. None with the return sample payload size of 120 kilograms proposed by some initial space mining company designs, but we'll assume instead of just the half kilo or less that NASA is grabbing off of an asteroid, we'll assume for the same cost the mining companies can grab their entire 120 kilograms. Now, the cheapest one we've been able to pull off was about $200 million in total cost, and that was the one that just flew through the tail of a comet to collect some ice. That wasn't one that actually landed on an asteroid and dug anything up like the Osiris Rex mission is going to do. The Osiris Rex mission is a fair bit more expensive, but again, we'll assume the mining companies can pull off the actual scraping stuff off an asteroid mission for the same price as merely the comet flyby mission. Now, assuming we only have to spend that much to get 120 kilograms of material, then we have to reach $200 million in revenue to break even, and thus obviously exceed that to start generating any profit. Now, some of the main asteroids being looked at by initial space mining hopefuls, the main asteroids being considered were platinum carriers. Some of those asteroids even estimated to be up to 40% platinum in their composition. So assuming a successful excavation and return of 120 kilograms to Earth, 40% of that would be about 48 kilograms of platinum, and for simplicity and fairness, we'll round that up to 50. So platinum is priced in ounces, as are most of the precious metals. So 2.2 pounds per kilogram out of 50 kilograms, that gives us 110 pounds of platinum, and 16 ounces per pound, so 16 times 110, that gives us 1,760 ounces of platinum. Now, platinum currently has been up and down around $1,000 per ounce, so assuming at the current prices, that would be 1,760 times 1,000, which basically just powers it up to $1.76 million, which is not even 1% of the cost of the operation. Now, even if we assume somehow the entire 120 kilograms is all platinum, so instead of 40%, the asteroid is 100% platinum, then obviously 100% is 2.5 times 40%, so multiply that revenue by 2.5, and that would yield $4.4 million, or a bit over 2% of the cost. So obviously, $1,000 per ounce won't cut it for space mining. But what if instead of platinum it was palladium? Or if the target element or material was the same price as palladium, which recently, although it fell back under it, hit new records of $2,500 per ounce. So assuming $2,500 per ounce, and 40% of the excavated material being your target material, since the first example was 1,000, all we have to do then is multiply that by 2.5 and get, again, $4.4 million, which again is barely over 2% of the operating cost. And then multiply that by 2.5 if we want to assume the whole 120 kilograms is target material. And that gets us $11 million, or 5.5% of the cost of the operation. So $2,500 per ounce still won't get anyone any profits. Now, what if we jump up to the level of rhodium? Rhodium recently exceeded $10,000 per ounce, working from a previous price of 2,500. Obviously, all we need to do then is multiply the numbers by 4. So 40% target material yield gets us $17.6 million, or a bit under 9% of the mission cost. In Fantasyland, with a 100% pure rhodium asteroid, all 120 kilograms in the return capsule being the target material, then we multiply again by 2.5 and get a yield of roughly $44 million. So at that point, you're up to 22% of the operation cost, but far from breaking even, and even farther from generating any actual net income. So even $10,000 per ounce won't get you anything back profit-wise. So let's jump up to finding out what actually would make the space mining missions viable. To do that, we have to go backwards now. 40%, 48 kilograms rounded up to 50 kilograms, is 1,760 ounces. Thus, we take $200 million divided by 1,760, and that brings us to a required minimum price, a break-even price of $113,636 per ounce of whatever you're mining. Yeah, unless it actually is unobtainium, that ain't happening. Now, what if the whole 120 kilograms was target material? Well, 120 kilograms is 4,208 ounces, so 200 million divided by 4,208 gives a break-even price of only $47,528 per ounce. So I said in a previous video that if we actually have to resort to asteroid mining, the required prices to make that profitable would thus make any product containing those materials beyond the unaffordability line for at least the majority of us. Just to show you an example, a computer contains about 1/40 of an ounce of gold. So assuming it's gold that you're asteroid mining, at even the 100% yield or lower space mining price, $47,528 an ounce divided by 40, or times 1/40, gets $1,188 as the material cost of that tiny amount of gold in each computer. So that would end you up with your cheapest possible computer prices on the shelf being likely between $1,200 and $1,500, as opposed to between $100 and $200 that you can see now. And that's assuming none of the other precious metals or rare earth metals that are needed in the computers have skyrocketed in price either. At the unfortunately more likely non-100% yield, at $113,636 per ounce, that's a minimum $2,840 on that computer price tag, which means the actual price would be up and over $3,000 minimum for any computer. Ain't nobody affording anything anymore in that world. Now, to be fair, private space companies have been able to bring down different kinds of costs down by about 40%. That percentage seems to keep showing up in outer space a lot. So we'll do a benefit of the doubt round and assume they can run the mining mission for only $120 million instead of $200 million. But even dropping down to only $120 million, that still requires a 40% yield price of $68,181 per ounce of whatever you're out there mining, and the Dreamland 100% yield price still needing consistently above $28,517 per ounce. Again, just to break even. Obviously, you need to go considerably higher if you actually want to generate any significant profits. Of course, you could always end up with a shale oil scenario where investor financing and debt readily flows in and continuously keeps non-profitable operations afloat, or are only generating profits in, say, the single-digit percentages. But that's a hypothetical, so regardless. So, is asteroid mining viable? Not really. At least not at anything close to current commodity prices. If anyone's actually going to be launching and trying anything in the immediate future, it's likely just going to be trying out different extraction methods and surveying target asteroids to see whether they are, like X% content gold or platinum or whatever. Also, even if prices actually do go that high, then yeah, it might be worth it, but even then it's still a really risky venture. Because it's not like a mining operation here on Earth. It's not like having a mining pit going on where even if it's in a remote region, you still have supplies coming in and out every day, if not maybe every week or so, where, one of your haul trucks breaks down or your mining excavator may break down, and you can just, send the mechanics down in the repair truck with some spare parts and fix it up. Whereas dealing with space, leaving Earth orbit, going out there doing orbital interceptions and returns, that takes years, multiple years. If anything goes wrong with that vehicle you send out there, that's it. It's gone. You just lost $200 million, and you just have to build and send out a new one. So even if commodity prices allow it, any potential mining companies would still have to actually consider it worth the risk. But we'll see what happens when and if it actually comes down to it. Or up and out to it, rather. So that's our quick little math session and overview of space mining potential. So thanks everybody for listening in or watching. Hope you all enjoyed yourselves. Please like the video if you did. Post it and share it around to anyone else or any groups that might be interested. Also, obviously, if you like hearing about energy and resources and mining operations, though usually we're talking about real ones down here on Earth, then please subscribe and stick around. Also, if you want to help me out or want to support me, then my PayPal link is down in the description below. I assure you, ad revenue does not pay well, unless you're in the big leagues getting millions of views. But that's it from me for now. May God bless you all, regardless of whatever becomes of me, and I will see you all around next time.